N-type material, right? Are you able to see the slide? So here the N-type material. So the majority carries are electrons. So if you apply a voltage across this device, the current will flow, right? Current through the silicon channel. So current will normally flow. And so this is without diffusion of P channels along the sides of the semiconductor materials. So here the P-type materials diffused along the either side of the material. So, so without this, suppose the gate voltage is zero. Gate voltage is made to zero. So current will flow through the junction or not? Current will flow through the channel or not? Current will, without this, I'm now we have the FET. So the FET has two PN junctions. So here this is one PN junction. This is another PN junction, right? So if gate voltage is made zero, and if so you are increasing the VDS, so what will happen? Let us assume that VGS is zero. It is shorted. That is, it's made to zero. On the application of VDS, current will flow through the device or not? From source to drain. Current flow will be there or not? When VGS is zero. Will there be any resistance for current? Yes or no? So current will flow through the material. So if you don't ask questions, I'll just explain and leave. So you have to ask questions. I don't know whether you are listening or not. I'm not sure. So if in case you have any questions, you have to ask me. Otherwise, I'll just explain and I'll complete my part. So you have to interrupt me if you have any questions. So current will flow through the device. So which is most of so the gate source is less reverse biased, right? In this case. So here you can see this gate voltage is zero. So gate voltage is zero means uh, which side is more reverse biased, which side is less reverse biased if VGS is zero. So gradually the current will increase. So you can see this on increasing VDS, there is a corresponding increase in the drain current. So you can see that there is a linear relationship between the voltage and current in this region. It is from region from A to C, where VGS is zero. So what will happen if you further increase this VDS? Uh, which junction is more reverse biased and which junction is less reverse biased? So you have connected positive supply to the N channel, right? So this junction is more reverse biased uh, than the source to gate, right? So what will happen? The depletion region increases. You can see the wedge-shaped curve. This is known as depletion region. So you can see this more depletion region is formed near the drain, whereas less depletion region is formed near the source. So you can see this wedge-shaped curve of the FET. So what will happen if you further keep increasing this VDS, the depletion region width increases. So when depletion region width increases, it restricts the flow of current. So you can see the constant current after this point. This point is known as pinch off voltage. Understood this point?
Yes, sir.
So this is how this so you can consider this FET is similar to your water tap. So when you tighten the tap, what will happen? The water flow will get reduced, right? When you tighten that tap. Similarly, when you increase the gate voltage, the current the current is reduced. So it is equivalent to your water tap mechanism. So when you increase the gate voltage, the current will reduce because so when you increase the gate voltage is reverse biased or forward biased according to this connection. Gate voltage is forward biased or reverse biased. Gate voltage is forward biased or reverse biased.
Forward.
Forward. See the diagram. Forward or reverse? VGS. Reverse bias. Yes, VGS is reverse biased. So when you increase the when the reverse bias voltage increases, what will happen? Depletion region gets increased and it narrow down the channel. Width of the channel is reduced, so it causes reduction of current. So this is the basic principle of field effect transistor. I think all of you have understood this basic mechanism of field effect transistor, right? Any doubt in this?
Yes.
So you can clearly see from this curves. So on increasing, so this is for VGS 0, this is VGS 0.5, this is VGS minus 1 because it's reverse bias 1.5 and 1.2. So for every increase in the VGS, there is a corresponding decrease in the drain current, right? Yes or no? So it's a voltage control device or current control device. If you compare this field effect transistor with BJT. So voltage control device or current control device. So we have plotted the same type of curve for the transistor in the last class. We have plotted collector current versus VCEC, that is collector supply. Here we plotted VDS versus ID. VDS is the drain source voltage, ID is the drain current. So what is the difference? What makes it different? If you compare the characteristics, it will be more or less same. Only thing here, what is the control variable here in case of FET? So voltage or current?
Voltage, sir.
Yes, voltage. Whereas in transistor, simple transistor, base current, right? For we have plotted the characteristics for various base currents, not the base voltage. So that is a basic difference between field effect transistor and the bipolar junction transistor. Bipolar junction transistor is a current control device. It's a voltage control device. Understood? So, so this is the circuit symbol of I'll show you the circuit symbol for first field effect transistor, and then I'll show you the circuit symbol of the. So I'll show you the operation of FET. So you can see here, see all of you please listen now. So here the VDS is applied, VDD, and so here this is VGS. The VGS is reverse biased. So we have connected negative polarity to the P type material, so it is reverse biased. So for small gate voltage, we can see the current. So if you increase the gate voltage, what will happen to the current? Drain current. Increase or decrease? So the depletion region width increases. You can see the increase in the depletion region. And what about the current?
Decrease, sir.
Decreased. So if you reduce the VGS further, you can see the corresponding increase in the drain current. So this is the basic mechanism. We have a N-type material over which the two P materials are diffused. So this forms the junction, and this electrical connection is made on the P-type material. So it is denoted as gate. This is source. This is drain. So without this P material, that normally the current will flow through the semiconductor as like just like as another device. But when you apply a reverse bias to the junction, that is this this causes increase in the depletion region, so it reduces the channel width. So there is a drop in the current. So you can see the drop in the current. So this is the basic mechanism of field effect transistor. So we are going to plot the characteristics, input characteristics as well as the transfer characteristics of the FET. And this is the simple circuit symbol of simple FET. That is source, gate, and collector. So we have P channel, and this is N channel. So you have to distinguish these two device using this arrow direction. And this is the characteristic curve for the, as I already explained, for VGS. So this curve is plotted for VGS 0. So for so up to pinch off voltage, you can see the linear increase in the drain current. At pinch off voltage, what happens? The gate source is more reverse biased than the drain to. That is, the drain to source is more reverse. Drain to the source is more reverse biased than the gate to source. That is VGS, VGD. VGD is more reverse biased. So depletion region width increases. So it levels of the current. So the current now becomes constant, and we can't operate this FET device after this breakdown point. The device will get damaged. And this is for VGS 0. Suppose if I apply VGS of -1 volt, what will happen? Current will increase or decrease? Current will increase or decrease?
Increase.
Increase. See, I said when you apply reverse bias, it creates a depletion region, then it abstracts the current flow, right? So the current will decrease. So you can clearly see from this diagram. So for VGS 0, this is VGS -1, VGS -2, VGS -3, and VGS -4, and VGS off. This is cutoff region. So we are going to basically plot this curve. This lab. Actually, our topic is MOSFET, not FET. Because you are not studied FET, so that's why I give some introduction to FET. Actually, actual topic is MOSFET. So this is the basic structure of MOSFET. MOSFET has two. Here there is no junction in MOSFET, so you can clearly see from this device there is no junction. And here the silicon dioxide is MOSFET. You can see the layer of silicon insulating materials, metal oxide semiconductor transistor. So this is metal oxide. So this forms the insulating insulator, and gate is one electrode, and this is one electrode. This substrate is an electrode. So what will happen? There is a insulation between these two electrodes, so it forms a capacitor. So when you apply voltage across this gate, whether it's a forward bias or reverse bias, accordingly it will creates charge carriers. When you apply a forward bias, it creates electrons in the in this region. And if you apply a reverse bias, it will create holes in this region. So when when you induce the opposite polarity carriers in the region between these two n plus, then it will create resistance for the flow of current. So this is the basic difference in the metal oxide semiconductor field effect transistor. So you can see the oxide coating, and this acts as an insulator between these two conductors. So it acts as a capacitor. So when you connect this positive supply on the gate, this becomes positive charge carriers, and here we have a negative charge carriers. So negative charge carriers, what will happen? When you it will increase the flow of current or decrease the flow of current.
Increase.
Yes, will increase the flow of current. It creates a channel and it creates current will flow. So the application of gate voltage increases the drain current. So that's why the name enhancement mode MOSFET. So MOSFET can be operated in both enhancement mode MOSFET as well as depletion mode. So in depletion mode means initially the device is off state, on state. When you apply a gate voltage, it will move on to on state. From there is on state to off state called depletion. Whereas off state to on state is known as enhancement mode. There is a basic difference between enhancement mode MOSFET and depletion mode MOSFET. And this is the circuit symbol. N channel depletion mode, P channel depletion mode, N channel enhancer mode, P channel. So these MOSFET devices are widely used in IC chips because packaging density of MOSFET is much greater than the transistor device. BJT occupies more area in the chip, whereas MOSFET occupies less area. So we always prefer MOSFET for the logic gates. Actually, your microprocessor basically consists of logic gates, right? All these gates are formed by using the MOSFETs. The MOSFETs are not actually used for amplification. It's actually used as a switch. Similar to your BJT switch, MOSFET is also performs because it's a three-terminal device. The application of gate voltage can turn on the device or turn off the device. So we can control the output current by the application of the gate current, gate voltage. So we can operate this as an inverter. So basically, this MOSFET is used in all the IC chips fabrication. Yeah, so we are so if you the current processor, Intel processor uses CMOS gates, CMOS gates. So all the NOT gate, OR gate, AND gate are realized using the CMOS gates. Complementary metal oxide semiconductor device. So it, more devices can be placed inside the chip. So you can increase the number of transistors in the chip. And this is the characteristics of MOSFET device. So actually we are going to do this experiment today. MOSFET characteristics. So this is a circuit diagram of MOSFET, and we are going to plot the input characteristics and output characteristics. This is the drain characteristic. This is the transfer characteristics. So for drain characteristics, we keep the VGS constant and we vary the VGS and note down the ID. So this is for transfer drain characteristics. And for transfer characteristics, we keep the VDS constant and we vary the VGS and we note the ID value. So this is the basic observations we make using this circuit. So you have to do both drain characteristics as well as transfer characteristics for this experiment. I'll show you the circuit diagram. So construct the circuit. I'll give you 10 minutes time. Construct the circuit. Once constructed, tell me. So any questions? Any questions? Do you have any questions?
No, sir.
Okay. Construct the circuit, I'll give you. Are you doing?
Yes, sir.
I'll also
Yes,
parallel.
sir. Yes, sir.
Okay, I'll also parallel do along with you. So you have to use the MOSFET. So NMOS, type NMOS. The MOSFET is, and you require two resistors. Voltage source. One
So what's the name of the component you said, sir? NMOS.
NMOS, yes. And correct is so the series resistance is how much? 220 ohm and 10 ohm. How to change the name of the source? V2, okay. V2 VGS. VGS. This is BDS. BDS. And this is 10 volt. This is 50 volt. Completed this part up to this.
No, sir. Could you wait a few minutes, sir?
Yes, sir. Okay. Huh?
Sir, could you wait for 2 minutes, sir? So we'll
No
complete
problem. You take 5 minutes. So no problem.
it. Okay, sir.
Once completed, let me know. So you have to take readings of train characteristics and transfer characteristics. So you have to do. So you keep the VGS constant. So so for this case, which is the first source? Which analysis we have to do to obtain this characteristics? Channels we have to do. What type of analysis in simulation setting?
Transient.
Not transient. It's DC sweep. DC sweep, right? So here, which is first source? So for first, let us consider train characteristics. So what is my first source? What is the second source?
So could you show all the values again, sir? So of the voltage and resistors.
You want to see that?
So the values of the voltage and resistors.
What do you want? I'm not getting
So
it.
in this, so in the circuits, the values that you have given for the resistors, can you show it once, sir?
220 ohm and 10 ohm.
Thank you, sir.
So for first analysis, for drain characteristics, which source will you take as a first source and which source as a second source? So you are going to keep the VGS constant. We have to vary this ID, VDS, and we have to note the ID current. It is our objective. For transfer characteristics, we have to keep the VGS constant. You have to vary the VGS and you have to note down the ID reading. This is the objective of this experiment. So we are going to plot the curve for these readings, and your graph will look like this. For every VGS increase, you can see the drain current. The drain current decreases because we are applying reverse bias. So for this drain characteristics, which is source act as the first source or which is source act as the second source? The DC sweep analysis. I'm asking DC sweep. Which one will you take as a first source? VGS or just tell me.
VGS.
So first source for drain characteristics, first source is VDS. Yes, a type of analysis is linear. Start value 0. Stop value. Increment order of 1. And for second source is PG. Yes. First source is VDS, right? VDS. Okay, let us see the response. Accordingly, we will modify. 0, stop value 10, increment of 1. 5, this is drain characteristics or what characteristics? Transfer characteristics. This is drain characteristics or transfer characteristics. Could you see the graph? Could you see the graph? Yes or no?
Yes, sir.
So here the VGS incremented by 1. So you can see there are 10 set of readings. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we will see the 10 set of readings. First, how it works, VGS will be set to 1 volt, and for this 1 volt, VDS will be varying from 0 to 30 volt and curve is plotted. And for second set of reading, again VGS will be set to 2 volt, and for 2 volt, this VDS is varying from 0 to 30 volt, and the corresponding curve is plotted. Understood? Understood or
Yes,
no?
sir.
So which is the topmost is how much volt? This red line, this topmost curve. So this is VGS 0. And what is the pinch off voltage? Can you tell the pinch off voltage? Pinch off voltage is coming as 7.9, right? So all of you please complete this. Once completed, let me know. Upload the snapshots.
Okay, sir.
Sir, can you run it once again?
Is what you want?
Can you show the run part once again? How to run?
Go to DC sweep. First source is VDS. This is for drain characteristics. So we are going to vary the drain voltage from 0 to 30 volt in steps of 1 volt. And we are going to keep the VGS constant. So VGS constant means 0 to 10 volt in steps of 1. So for first, the response will be plotted for 0 volt. VGS 0 volt, 0 volt. And the first source will be varied from 0 to 30 volt in the steps of 1. You will get the curve, this red color curve, the topmost one. In the second iteration, what is my VGS for second iteration? Second reading. What is my VGS? First is 0 volt. Second is 1 volt, right? So for 1 volt, VDS will be varied from 0 to 30 volt in steps of 1. And you will get this curve. That is the pink color curve, this curve. Have you all understood this, how this works?
Yes, sir.
So plot the curve and find the pinch off voltage. Tell me the pinch off voltage. We all got this curve. Please upload the answers. Please upload the graphs. We'll do the second one. Once completed, do the second one. I'll give you 10 minutes time. Anyone did transfer characteristics? So for transfer characteristics, being approved. So which one is first sources? PGS. It is 10. Second sources, PDS. Note is increment of one. Okay, one more. Now let us see the characteristics. Brain characteristics of the device. So here the x-axis is 10 volt. It is 0 to 10 volt because we have taken the first source as VGS and second source as VDS. And so here we initially set the VDS constant. So VDS is initially 0 and VGS is varied and the curve is plotted. The second iteration, we keep this VDS as 1 volt and we increase this VGS from 0 to 10 volt in steps of this yes 0 to 10 volt in steps of 1 and we got this second curve. So we can change this increment level also. Can we verify this? 0.1. 0.1 is coming. Brain characteristics.
Yes, sir.
Sir,
We can upload the snapshots chat box.
Uploaded, sir.
Naman Kumar, so many of you have uploaded. So this is transfer characteristics. Okay. We would invoke. Have you noted pinch off voltage from the drain characteristics? What is pinch off voltage? So this is pinch off voltage. You can see this curve. The line intersecting the VDS, at which the current is constant. Drain current is constant. So this point is known as pinch off voltage.
Sir, it was 1 milliampere.
Which one is one? I'm voltage. The pinch off voltage. You are saying ampere.
Okay, sorry, sir.
Hmm. Next thing, you can try this. Can verify the operation of MOSFET as a switch. See, last class we did transistor switch. So you can verify the operation of MOSFET as a switch. Last class we did or not? Transistor switch. You remember? Yes or no? So next you do MOSFET switch. Switch means I'll show you the MOSFET switch. A switch operation. Okay. Let us make this input voltage as 0. Input voltage is 0. So what is the output? For input 0, what is my output? So go to the edit simulation tool. Edit simulation tool. Which analysis you have to do? Transient analysis. So uptimers. 30 seconds. Are you getting 1 volt? That is 30 volt output for 0 input. Now, if I made this as 5 volt, let us see the response. Output is still 29. Yes.
So for input, it's coming 30 volts. So input 0, it's coming 30 volt.
30 volt, that is on. Transistor is on. How will you make it off? You have to apply. How you turn on the transistor? It's minus. It's not too much. 10 volt. Each of voltages. Anyone did MOSFET switch correctly? Open is coming same voltage. Nice. Even Federer did switch. Okay, do the switch in the next class. It's not working properly. Output voltage should come 0. Okay, I'll tell you this switch in the next class. All of you upload this MOSFET Cat6 for this class. I upload the PPT now. If you got the PPT of MOSFET,
Yes, sir.
please prepare the lab report for this class, and I'll create a link today and you can upload it. Up to the, so I think we have completed 6 experiments so far. BJT Cat, BJT amplifier, MOSFET Cat6, and voltage regulator, and band pass filter, and rectifiers, diode characteristics. So if you have any questions, you can ask me. Otherwise,
Sir, what will be the due date?
due date normally 1 week.
Okay,
Pay.
sir.
So all are having the lab report for the completed experiments. I think I've given the format also. So please follow the format, and I'll create a link today. So you can upload it.
Sir,
Yes, tell me.
sir, you said you'll send the manual for the first experiment alone.
What manual you want?
For the first experiment.
First experiment. Okay, now it will file. Okay, I'll upload it. Band pass filter, I'll upload it. Because I
When
need
is the deadline, sir?
1 week. 1 week from now. That is next week. Before coming for the next class, you need to upload it. Is that fine? You want more time?
Sir, could we keep next weekend, sir?
Okay, next week. Okay, I'll extend 2-3 days. That does not matter. But I think I've sent a list of experiments in the last class itself. So we started with the band pass filter, and we went out to do diode characteristics and diode rectifiers. And third class we did BJT, that is voltage regulator. And then the fourth class BJT characteristics, and fifth class BJT amplifier. This is sixth class. This is MOSFET. I'll show you the amplifier and switch in the next. We'll do MOSFET amplifier and MOSFET switch in the next class. Because it's not working. I need to check the. Okay. We done the transistor switch. Last class I explained the transistor switch. Okay, if you have no questions, you can. Let me check the attendance. So all are present. Thing. So once completed, you can leave. If you have any questions, you can stay back and ask. Those completed can leave.
Thank you, sir.
Thank you.
Thank you, sir.
Sir, have you taken attendance?
Attendance from I'll download it.
Thank you, sir.
Thank you.
Thank you.
Thank you, sir.
Thank you. Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you all.
Thank you, sir.
Thank you. So no questions, I'll leave.